Hey Math Club, this is Noah with a Math Club video bonus. In our last episode, Finding Primo, Pete explained a couple of tests that mathematicians use when trying to decide if large numbers are prime. We thought it might be helpful to see the math written down, so without further ado, let's get to the tests. Would it be okay, Pete, if we kind of took a step back, circled back around, and maybe chose a much, much smaller and more approachable number to sort of put to these tests and see how they play out?
Yeah, let's try it with 2 raised to the 5th power minus 1. So now that happens to be 31. Let's move on to this probably prime test. Okay, so let me explain how this is supposed to work. We start with a candidate number that we want to test for primality. So what we're going to do now is this. We'll pick a base number that's less than our prime candidate. Then we'll subtract 1 from our prime candidate and raise this base number to that power.
Okay.
And then finally, we'll divide our prime candidate into the result and check what the remainder is. And if the modulus is prime, and you perform this exponentiating that we're doing, where we raise it to the power that's 1 less than that prime, every remainder should be equal to 1.
All right. So how do we apply this to trying to figure out if 31 is prime?
Right. So in this case, we're going to set the modulus P equal to 31. And that's the number we're going to use when we do this division and look for the remainder. Now, if 31 is prime, when we do this process, every remainder should be equal to 1.
Gotcha.
So go ahead and choose a base number, any number less than our candidate number of 31.
Let's go with 2 for the base number. I have a feeling these numbers are going to get really big.
Yeah, we have to raise these numbers to the 30th power now, right? 1 less than 31 is 30. That's our exponent. So I'm going to raise 2 to the 30th power. I ended up with something slightly bigger than a billion. 1,073,741,824.
And now we're going to divide that by 31 to see if we get a remainder of 1?
Exactly. And if I do that, the quotient is 34,636,833, but it leaves a little bit left over. And if I ask what the remainder is using that quotient, lo and behold, I end up with 1.
All right. So if we had gotten anything other than 1, that would rule out the possibility of 31 being prime. The fact that we got a remainder of 1 tells us we're still on track. It still could be. So now we should try 3 instead of 2 and see if we get another remainder of 1.
Yeah. Okay. So 3 to the 30th. It's 2 times 10 to the 14th power. It's got some other digits in there, but it's a very big number. However, 3 to the 30th, if I divide by 31 and look for the remainder, once again, I get 1.
All right. So we just checked 2 and 3. We got remainders of 1 for both.
I think we're going to say this number is probably prime. And then we would proceed to the next step,
which is the Lucas-Lehmer test.
Yeah, the Lucas-Lehmer test is actually really interesting.
How does it work?
First, we're going to build out a sequence of numbers, and that sequence will be the same no matter what our prime candidate is. And we make this sequence as follows. We start with a seed value, in this case, the number 4. We square it and subtract 2. That gives us the first term in our sequence.
Well, if we square 4, we get 16, and then subtract 2 brings us back down to 14.
Great. That's the first term in our sequence. Then we square that and subtract 2 to get the second term. And we keep going just like that, squaring each term and subtracting 2 to get the next one. So what does that give us?
All right. So 14 squared is 196. Take away 2, and that leaves 194.
Perfect. Okay. Now, to get the third term in the sequence, we would repeat the process, square 194 and subtract 2.
I happen to know that 194 squared is 37,636.
All right. So the third term in the sequence ends up as 37,634 because we have to subtract 2, right?
Okay. And what are we going to do with this sequence?
Well, remarkably, we only need to use one of the terms in this sequence to perform the Lucas-Lehmer test. And our prime candidate, the Mersenne number that we're looking at, it tells us which term to use.
Oh, that's interesting. How does it do that?
Well, we look at the exponent that 2 was raised to in order to create that particular Mersenne number. Subtract 2 from it, and that tells us which term in the sequence we should look at. So now the Mersenne number, whose primality we're trying to establish, is the number 31, right?
Right.
And what is the prime exponent that is associated to that Mersenne number?
Well, does that mean 5 because that Mersenne number was 2 to the 5th minus 1?
That's right. The prime exponent in this case is p equals 5. Now, we have to subtract 2 from the prime exponent. And in this case, we get 3. So in this case, we can look at term 3, which is 37,634.
All right. And what do we do when we're looking at it?
We ask, does our candidate Mersenne number 31 divide evenly into 37,634?
31 times 1,214 would give us that value.
That's right. This third term in the sequence, 37,634, can be factored with 31 as a divisor. This means that 31 is prime. It's that simple.
That's it, Math Club. We hope this video bonus was helpful, and we look forward to seeing you next time.